Hi students, in this lecture we are going to study about some of the very important properties of conjugate of a complex number. Further, we are also going to see some of the very important theorems and properties associated with the modulus. Also, we are going to understand all these properties and theorems by solving some problems. Earlier, we have seen what is conjugate of a complex number. Now let's try to understand this concept in detail. Let us say that we have a complex number z equal to a plus iota b. Now, the conjugate of this complex number would be represented by z bar equal to a minus iota b. We replace this positive sign by a negative sign. If the complex number was a minus iota b, then the conjugate would be a plus iota b. Simply the sign changes. Plus becomes minus and minus becomes plus. Now let us say that we have an eigenplane in which this represents the real axis and this represents the imaginary axis. This is the origin. Now let us say that this is a complex number z. We have represented this complex number in the eigenplane. Now the conjugate of this complex number would be symmetrical about the real axis, or it would be the reflection of this complex number about this real axis. Thus this becomes the conjugate of z. We can clearly see that z bar, or the conjugate of z, is symmetrical about the real axis. Thus if we have any complex number z equal to a plus iota b, then its conjugate would be a minus iota b, and this conjugate would be the reflection of the complex number about the real axis. Now let's study some of the very important properties of the conjugate. The first is the conjugate of z conjugate is equal to z. So if we take the conjugate of the conjugate, then it would give the original complex number, which is z. The second is, if z is a purely real number, then z is equal to z conjugate. So if any complex number is purely real number, that is the imaginary part is equal to 0, then the conjugate of that complex number would be the same as the original complex number. So z is equal to z bar. If z is purely imaginary number, then the real part of z should be equal to 0, and so z would be equal to minus of z conjugate. The next property is the real part of z is equal to the real part of z conjugate, and this is equal to z plus z conjugate divided by 2. So the real part of z is equal to z plus z conjugate divided by 2, and this is also equal to the real part of z conjugate. Similarly, the imaginary part of z is equal to z minus z conjugate divided by 2i. So the imaginary part of any complex number could be written in terms of z and z conjugate as z minus z conjugate divided by 2i. So the real part of z is equal to z plus z conjugate by 2, and the imaginary part of z is equal to z minus z conjugate divided by 2i. The next property is, for two complex numbers z and w, let's take two complex numbers to be z and w, then the conjugate of z plus w is equal to the conjugate of z plus the conjugate of w. So if we have got any two complex numbers z and w, then the conjugate of the sum of z and w is equal to the sum of conjugates of z and w. That is, z plus w conjugate is equal to z conjugate plus w conjugate. The next property is, for two complex numbers z and w, we have the conjugate of z minus w equal to z conjugate minus w conjugate. Simply, the conjugate of the difference of two complex numbers is equal to the difference of conjugates. The next is, for any two complex numbers z and w, we have the conjugate of z into w equal to z conjugate into w conjugate. We can simply write the conjugate of the products as this way. The next property is, for two complex numbers z and w, we have the conjugate of z bar w equal to z conjugate divided by w conjugate. So again we can say that the conjugate of division of two complex numbers is equal to the conjugate of first complex number divided by the conjugate of second complex number. The next is, the conjugate of z to the power of n is equal to z conjugate to the power of n. So this is also a very important property, that the conjugate of z to the power of n is simply equal to z conjugate to the power of n. The next is, for any non-zero complex numbers z, we have the conjugate of 1 by z equal to 1 by z conjugate. Simply the conjugate of 1 by z is equal to 1 upon z conjugate. And the last property is, the modulus of z is equal to the modulus of z conjugate. So the modulus of z is equal to the modulus of the conjugate of z. So these were some of the very important properties of conjugate. Now let's look at theorem number 1. It says that let P be a polynomial with real coefficients of degree n. Then if a complex number z is its root, then its conjugate is also the root of the same polynomial equation. It says that if we have a polynomial equation with real coefficients of degree n, so P is an n degree polynomial. Now if z is a root of this polynomial equation, then z conjugate must also be the root of the same polynomial equation. So let's look at the proof of this. Let us say that the polynomial equation P of x is equal to a0 into x to the power of n plus a1 into x to the power of n minus 1 plus a2 into x to the power of n minus 2 and so on up to an, where a0, a1, a2 and so on are real numbers. Now let us say that z is a root of this polynomial equation. Now if z is a root of this polynomial equation, then P of z should be equal to a0 into z to the power of n plus a1 into z to the power of n minus 2 plus a2 into z to the power of n minus 2 and so on up to an should be equal to 0, as z is a root of this polynomial equation. Now what we do is, we take conjugate on both sides of this equation. When we take conjugate, what we get is P of z conjugate equal to the conjugate of a0 into z to the power of n plus conjugate of a1 into z to the power of n minus 1 plus conjugate of a2 into z to the power of n minus 2 and so on up to the conjugate of an, and this should be equal to 0 because the conjugate of 0 is equal to 0. Now using the properties of conjugate which we have just seen, we can write this equation as P of z conjugate equal to a0 into z conjugate to the power of n plus a1 into z conjugate to the power of n minus 1 plus a2 into z conjugate to the power of n minus 2 and so on up to an equal to 0. As an is a real number, therefore its conjugate would be an. What we observe here? We observe that the conjugate of z is also a root of P of x. So z conjugate makes the polynomial equation equal to 0 when we substitute z in place of x. Thus we can say that z conjugate is also a root of P of x. So we have proved this theorem that if z is a root of a polynomial equation, then its conjugate must also be a root of the same polynomial equation. Now let's look at theorem number 2, and which is also known as the parallelogram identity. What does this theorem say? It says that let z and w be two complex numbers, then we have modulus of z plus w whole square plus modulus of z minus w whole square equal to 2 times the square of modulus of z plus the square of modulus of w. That is, the sum of the squares of the lengths of diagonals of a parallelogram is equal to the sum of the squares of lengths of all the sides. So this identity says that if we have any two complex numbers z and w, then we have the relation that modulus of z plus w whole square plus modulus of z minus w whole square is equal to 2 times the sum of squares of modulus of z and modulus of w. When we look this identity from the parallelogram point of view, then we can say that the sum of the squares of lengths of diagonals of a parallelogram is equal to the sum of the squares of lengths of all the sides. So let's once again look at the proof of this theorem. Let's first of all look at this value, which is modulus of z plus w whole square. Now this could be written as z plus w into z conjugate plus w conjugate. We have earlier seen that modulus of z square could be written as z into z conjugate. If we take the conjugate of this complex number, this would be z conjugate plus w conjugate. So we can write this as this way. When we multiply both these factors, what we get is z into z conjugate plus z into w conjugate plus w into z conjugate plus w into w conjugate. This is nothing but square of modulus of z, square of modulus of w, and this term is actually equal to 2 times the real part of z into w conjugate. So the square of modulus of z plus w is equal to modulus of z square plus modulus of w square plus 2 times real part of z into w conjugate. Now let's look at the value of modulus of z minus w whole square. This is equal to, we can write it as z minus w into z conjugate minus w conjugate. We use the same logic as we used here. Again, we multiply both these factors. What we get? Z into z conjugate minus z into w conjugate minus w into z conjugate plus w into w conjugate. Again, we see that z into z conjugate is the square of modulus of z. Similarly, this term is the square of modulus of w, and this term becomes minus 2 times real part of z into w conjugate. So modulus of z minus w whole square is equal to square of modulus of z plus square of modulus of w minus 2 times real part of z into w conjugate. Now we add both these terms. What we get? Modulus of z plus w whole square plus modulus of z minus w whole square is equal to 2 times modulus of z square plus modulus of w square. Both these terms gets cancelled and this becomes double. So thus we have proved that the modulus of z plus w whole square plus modulus of z minus w whole square is equal to 2 times the square of modulus of z plus square of modulus of w.